So far we have been talking about general linear operators between Banach spaces, and we derived a criterion on invertibility. Now we're going to talk about special case, which is encountered in practice a lot. So our Banach space is going to have a special structure. First of all, x and y are equal to each other, and both will have this special structure V cross Q, and both V and Q are reflexive Banach spaces. Then we consider bounded linear operators A from V to V prime and B V to Q prime, and our operator equation is here. It has this structure. The unknowns are U and P, the given right hand side F and G. You can write this also as one operator equation in this way. So the A bar is going to denote the resulting linear operator. Now we can also write this in terms of some bilinear forms. Bilinear form small a and small b given this way. So for example, small b will be acting on V and Q, right? V and Q. And in terms of these bilinear forms, we can write our operator equation here. You can also write, if you want to find what would be the bilinear form corresponding to A bar, this big operator, then the bilinear form would be this. So the unknown x it consists of two components, U and P, and the test, let's say the test function y, that will also consist of two components. So we want to, since we have a general criterion on the invertibility of A bar, we just want to see how that condition translates to a condition in terms of A and B, okay, or small a and small b. So let's say first let's just assume that A bar is invertible, and then we try to find some condition on A and B. Then we try to show that that condition is actually sufficient also to prove that A bar is invertible. So since A bar is invertible, we have bounded below property for A bar, and we can write this property in this way. Since VQ together is one variable for A bar, right? So just put U equal to 0 in this condition. So if you do that, because U is 0, this term will disappear, and that term will also disappear. On the right hand side, you will have this U disappearing. So as a result, we get this condition. And you can see that since there is V plus Q here, in order to take supremum, we should take Q equal to 0. So you just put Q equal to 0, and that gives us this condition here, some type of inf subcondition for the bilinear form B. You can also read this as the left-hand supremum as the norm of B prime applied to P. So this is simply the condition that says that the B prime is bounded below. So this will be one important condition. Okay, B prime bounded below. You can also think of it in this way directly also, just in terms of the bilinear form B. Okay, now we want to derive something on A, right? We have condition on B now. So suppose A bar is invertible, so that's our condition. And let's just write the first equation of our system. So the first equation is AU plus B prime P is equal to F. You can of course write this in this way, in the variational form. And if you restrict V to the kernel of B, okay, so let's remember that B, where this B is acting on V and sending this to Q prime. So that means the kernel of B will be a subspace of V. Kernel of B is a subspace of V. So if you restrict to the kernel of B, this term will be 0. So it gives us this equation here. AUV equal to FV for all V from the kernel of B. And that tells us that U depends only on the right hand side F restricted to the kernel of B, because the other equation depends only on the right hand side G, not on F. Okay, so we want to, inspired by this, we want to define this A0 operator that acts on kernel of B and sends it to kernel, the dual of kernel of B, by simply restricting U and V variables to the kernel of B in the bilinear form A. And what we want to show is actually that this A0 is invertible. So we want to construct the inverse of A0 directly, and this E is going to be actually the inverse. So we define this E by solving this equation here. Since A bar is invertible, we can solve this equation. And F, so the right hand side is F and 0. Given that, we find, let's say, U and P, right, as the unknowns, and we call this U part of this unknown as EF. So we restrict our right hand side to the dual of the kernel of B. So this says that EF is well defined because it does not depend on how we extend F from the dual of kernel of B to the dual of whole space of V. Why this is so? That's because we saw here that U depends only on the restriction of F onto the kernel of B. So in other words, EF is simply you solve the system of equations with right hand side F0, and well, first of all, you can extend this F into an element of V prime any way you want. Then you apply the inverse of A bar, then you project onto the first component, meaning you just simply take the first component. So that's basically that's what we have for EF. Now the second equation, because the second component is 0, that gives us B times B applied to EF is 0. That means EF is in the kernel of B. So E is actually sending the dual of kernel of B into the kernel of B. So there is a chance that B is actually the inverse of A0. So let's check that. Okay, so take the test function V in the kernel of B. Then we just write our equation. So A0 applied to EF tested against V, because EF is already in the kernel of B, it is equal to this by definition of A0. Then we write the definition of EF. So EF would be just F minus B prime P, right? And by the definition, we put B prime over to the other side so that we have BV here, and use the fact that V is in the kernel of B to conclude that this part is 0. So it's just FV. And it shows that A0 applied to EF is equal to F, or in other words, E is just the inverse of A0. So to conclude, we have this implication, A bar invertible implying two conditions. First, A0 is invertible. A0, basically we defined it as something that acts on the kernel of B, or part of A that acts on the kernel of B, and the B prime is bounded below. Now quantitatively we can also see that the bounded below constants of A0 and B prime, meaning that for A0, for example, since A0 is invertible, the bounded below constant would be just related to the norm of the inverse of A0. And we can see that the inverse of A0 is E, and E is directly related to the inverse of A bar. So the norm of the inverse of A0 is directly related to the norm of the inverse of A bar. So that constant for A0 depends on, or not worse than, that constant, the corresponding constant for A bar. And B prime, we also saw that the constant C is not worse than the corresponding constant for A bar. Okay, so now we want to show that assuming A0 invertible and B prime is bounded below, we want to show that A bar is invertible. That's the other side. So suppose A0 is invertible and B prime is bounded below. We want to show that A bar is invertible, right? That means given F and G, we simply want to solve this system of equations. So we will construct solution U and P in a few steps. First, we define this W that acts on the range of B prime. It's a linear functional by this formula. We can write any element in the range of B prime in this way, and we can at least define a linear functional on the range of B prime by this formula, right, for all Q in Q. And after that we can show that this functional is bounded by using the bounded below property of B prime. So basically we try to bound this and use the right hand side to write that it's bounded by G times Q, and then use the bounded below property of B prime to bound Q by some constant times B prime Q. And B prime Q was our object here, or the argument of this W. So this shows that W is indeed in the dual of the range of B prime. Where is the range of B prime, right? So B prime is acting where B prime is acting on Q and sending it to B prime. So that means the range of B prime, so that means range of B prime is a subset of V prime. So we can actually extend this W into an object in V double prime, and V double prime is equal to V. And if you extend that way, we can see that if you look at the definition here, just put B prime over to the other side, we see that BW is equal to G. Because G was any element in Q prime, it says that that any element in Q prime can be written as BW. That means B is actually surjective. Okay, so we have this W. At least we have, basically we can solve the second equation here. And now we want to look at the first equation. So we're going to solve this equation. Okay, so here U hat is the unknown function in the kernel of B, and with this right hand side f minus aw, v is in the kernel of b, the test function. So here what we're really doing is we are inverting a0 here with the right hand side f minus aw. We can do it because a0 is invertible. Okay, and now we can also read it in this way. So if you put this a u hat over to the other side, it says that f minus a times u hat plus w is actually in the annihilator of the kernel of B, and the annihilator of the kernel of B is equal to the range of B prime, because B prime is bounded below, so the range is closed, right? And so that's because this is in the range of B prime, and B prime is injective because it's bounded below, we can solve this equation now. So with the unique solution P from Q. So we can write this. So if you call this u hat w, then we see that it simply says that au plus b prime p is equal to f. So that's actually our first equation. So the first equation is satisfied. Now we can check the second equation. The second equation was satisfied with w, but we modified that w by adding u hat. So let's check if that will change anything. So we check bu, okay, bu is equal to bw plus bu hat, but it doesn't change anything because u hat is in the kernel of b. So bw plus bu hat is equal to bw, and bw was equal to g. So we have solved our equation. There exists indeed for any given f in v hat and g in v prime and g in q prime, there exists unique solution u in v and p in q, satisfying this system of equations. So we proved both sides of this implication. A bar is invertible is equivalent to saying that A0 is invertible and B hat is bounded below. Now we can also try to estimate the relevant or constant, or let's say the norm of the inverse of A bar in terms of the constants of A0 and B hat. B prime. Okay, so we just need to estimate these various norms of w and u hat and p that was just in the previous slide. So first of all, we can estimate w by this. To estimate the norm of w, we just simply need to look at this estimate here. It immediately says that the norm of w is bounded by beta times the norm of g, and this beta is the bounded below constant of b prime. Okay, so we have this estimate on w. Now what about u hat? Well, u hat was defined by this, so it just simply means, so the norm of u hat is simply bounded by alpha, so I call this alpha is now the norm of the inverse of A0, and that's bounded by alpha times f minus aw, and we have this bound on w, so that we have this bound on u hat. And what is u? U is u hat plus w, so we have this bound on u in terms of f and g. And finally p, let's see how it is defined. So p was defined by this equation. So that means basically whatever we have in the right hand side, the norm of that will be multiplied by the bounded below constant of b prime. So the bounded below constant of b prime is alpha. So again, substituting everything into this, we get this estimate. So we can see that the constants are here, this alpha and beta times the expression in the bracket, and over here these constants here, those would be would give us the norm of the inverse of a bar here. In other words, that constant of a bar bounded in terms of the bounded below constants of a0 and b hat, b prime.